let's talk a bit about the division algorithm. So, this is essentially the following thing. What we said is we can get, when we divide one number by another, you get a quotient and a remainder. So, you get two different things. So, if I have say A and B are two numbers, then the division algorithm says you can find unique Q and R such that R is a number between 0 and B, Q is some natural number such that A can be written in this form, right. So, let us just think of it with an example. Let us just look at what this does. Suppose I take the number B equal to 7 and then see what happens when I try to divide every natural number by 7. Okay. So, what happens? So, let me for the moment just focus on the kinds of remainders that I obtain through this process. So, let us start writing out the various natural numbers. So, I go in sequence 0, 1, 2, 3, 4, 5 and so on, and when I divide each of these, the first 6 numbers that I wrote out here, by the number 7, then the remainders I get. So, the quotients I get in these cases are all 0. So, all these numbers that I wrote out here, so B7 this example. So, everything I wrote out here has quotient 0, because when you divide them by 7 you do not get a quotient, and the remainders themselves are are the same numbers here. So, this is, if I take 0 it is remainder 0, if I take 1 it is remainder 1 and so on. So, these are the various remainders I get. So, what I am going to do is to start forming a table here of various remainders. So, this is remainder 3, 4, 5 and so on. So, now if you, let us see what happens when you go to the next number, which is 7. So, 7 when you divide by B, which is 7 again, the remainder is 0, the quotient is 1, right. So, the remainder is still a 0, so I am here, but now the quotient has increased. So, the quotient is 1 now.
So, the first column of your table will have all the numbers with remainder 0?
Right.
Okay.
Exactly. So, the first column is going to have everything with remainder 0, the second column is going to have everything with remainder 1 and so on. So, for example, this is 8.
That's okay. So, 8 has remainder 1,
8 has
9
quotient 1 and remainder 1.
9 would have remainder 2, 10. Okay, so it just goes along
12,
like that.
13 and so on, and now again when you reach 14, then you see that the quotient increases. The quotient is now 2, the remainder is back to being 0. 15 has remainder 1, remainder 2, remainder 3, 4, 5, 6 and so on. Okay. So, what we really have done at this point is the following. We have taken the set of all natural numbers. We could also do this with all negatives, the negative integers, but for now we are looking at all the whole numbers, trying to divide them by 7 and trying to think of these two pieces of information that you get out of it. One is the quotient, the other is the remainder, and using them, so we are trying to draw this in the form of a table.
This reminds me of a clock, right. After 12 hours it resets back, AM changes to PM and then it resets back and then the date changes, and so it is like it keeps repeating again and again,
right.
And each time you change. That is a 12-hour clock, and here it seems like you have something very unusual, a 7-hour clock.
Right, exactly.
Oh look, so here is a 7-hour clock, and you start with 0 and then 1, 2, 3, 4, 5, 6 and you come back to 0.
Right, exactly. Now, if you did this on the number line, which is with all integers,
right,
then things work a little differently, right. So, what happens when you sort of increase by 1 each time on the number line?
So, you just keep moving, right, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and it just keeps going, you never come back.
You never come back. So, you just keep going on and on in a straight line, whereas here when you think of taking the remainders by when you divide by 7, what keeps happening is you keep coming back to 0 each time, right. So if you only keep track of the remainders that you get when you divide by 7, then it is like a clock, just with a clock with only one hand, which keeps sort of coming back again and again to 0. But we also have the quotient, remember, right. So each natural number gives you a remainder when you divide by 7, but also there is a quotient, and if you put these two things together, then you can view the natural numbers as being a cylinder rather than a number line.
A cylinder. Okay, so here I have this table of numbers. The rows are the quotients. So these are quotient 0, quotient 1, quotient 2. The columns are the remainders, remainder 0, remainder 1, remainder 2. But really we should be thinking of this as a cylinder of numbers, right. So what is happening over here? A cylinder like this,
right.
So after 6 you go up one level, and so from 6 you go up to 7, from 13 you go up to 14,
right.
And the numbers are really forming a cylinder rather than a rectangular array.
Right. So this way of organizing the integers or natural numbers in the form of a cylinder, where we keep track of quotients and remainders, or we could just keep track of remainders alone, in which case you are thinking of it like just like a clock, okay. You are ignoring the quotients. So let us start with that point of view. So this particular notion is very important, and it goes all the way back to Gauss, who we talked about right at the very beginning. So let's define this notion. It's called congruence. So it says two integers, so let B be a natural number. So two integers x and y, we say that x is congruent to y modulo b. So all these different words here. So one is congruent and the other is modulo. If the following happens, if x and y leave the same remainder, when divided by b. Okay, and this is the thing that we were keeping track of. For example, if you take b to be 7 and you took two numbers, say 6 and 13, then observe both of them give you remainder 6 when you divide by. So this is 0 times 7 plus a remainder of 6. 13 was 1 times 7 plus a remainder of 6, and these were in fact exactly the numbers that, these sorts of numbers were the ones you write along a column of the cylinder, for example. Okay. Now there is a notation for this. So we write, the notation is, we say that x, so we write these three lines, read it as congruent to, so x is congruent to y mod b. Okay, so this is the notation for this definition. Okay. Now we looked at these examples here. Let me give another one for a different choice of numbers. So suppose I take p equal to 7 again. Now let us look at some negative numbers. So if I take x to be minus 3 and y to be 4, then again x and y are congruent to each other modulo 7. Okay. So let us check this. So we haven't really looked at many examples with negative numbers. The number 4 is easy, quotient is 0, 0 times 7 plus a remainder of 4. Now if you try to do this minus 3, recall the remainder is supposed to be a number between 0 and 7, right. So how do we write minus 3 as some multiple of 7 plus a remainder between 0 and 7? Well, the way to do it is this, minus 1 times 7, so that is a minus 7 plus a 4. So, in fact, the remainder that minus 3 leaves on division by 7 is also the number 4. So, we would express this by saying that minus 3 is in fact congruent to 4 mod 7. Okay. Likewise, the earlier example says 6 is congruent to 13 mod 7. Okay. So, these are all examples. Now, let us write out the following simple lemma, which gives us a quick way of checking that two numbers are congruent to each other modulo b. Instead of actually finding the remainders themselves, so x is congruent to y mod b if and only if. So, recall this is a symbol for if and only if x minus y. So, you take the difference between the two numbers, then that has to be a multiple of b. Okay. So, recall this happened in all our examples. So, if you had 6 and 13 for instance, if you take the difference between those two numbers, so let me do it like this, 13 minus 6, that was 7, and that is of course divisible by 7. Likewise, the other example we had minus 3 and 4, if you take the difference between those two numbers, minus 3 minus of 4, that is minus 7, that is again divisible by 7. Okay. So, instead of verifying what the remainders are for each of them and checking that they are the same, it is enough if you just take the difference and see that it is a multiple of the number b. Okay. So, let us prove this. It is a very easy proof. So, when we have an if and only if assertion, what you have to do is to prove that both directions hold. So, we assume what is given on the left and prove what is given on the right. Likewise, you assume what is on the right and prove what is given on the left. So, let us prove the forward direction. So, we are going to assume that, or this is what is given, that x is congruent to y mod b according to the definition, and from that we have to try and prove that x minus y is a multiple of b. So, let us do this. What does it mean by definition to say x is congruent to y mod b? This means that when you write x using the division algorithm, you get some quotient and some remainder. We do that with y, you get some other quotient possibly, but the same remainder. Okay. So, the remainder r is the same in both cases, some number between 0 and b, and so when you subtract x minus y, the r's cancel and you just get q1 minus q2 times b, which is of course a multiple of b. Okay. So, this is the proof of the forward direction. So, let us prove the converse. So, if we assume, so for the converse what is given, we can assume that the difference is a multiple of b. So, let us say it is some m times b for some number m in z for some integer. Given this, we have to figure out that the remainders that x and y give you are the same. Okay. So, let us do the division algorithm. So, let us write x first as some multiple of b plus some remainder. I have to check that y also gives me the same remainder. Okay. So, let us calculate y using what is given. So, y is nothing but x minus mb. So, I will rewrite it as qb minus mb. So, that is q minus m times b plus r. Okay. But now observe that this is nothing but what have I done? I have written y in the form of some multiple, let us call that multiple as q prime b plus r. Q prime is some integer and r is some number between 0 and b. So, I have managed to do this, right. I found one expression for y in this form. Now, by the uniqueness, this is the very important aspect of the division algorithm, that if you find a quotient and a remainder where the remainder satisfies this property, then the quotient and remainder are unique. Those you can only find one such pair q and r which satisfy this property. So, by the uniqueness property of the division algorithm, the remainder that y gives you on division by b is exactly r. Okay. So, R is exactly the remainder. When Y is divided by B. So, that proves the reverse direction as well, the converse. Okay. So, this gives us a very quick way of checking when two numbers are congruent to each other.